It's like a problem I assigned. Okay, so for number 21 and 8.7, they have y double prime plus y is delta t, and y of 0 is 1, and y prime of 0 is minus 2. Right? Okay, so firsty things first. What do you do? Yeah, the tool you have for solving delta things, or unit step things, or discontinuous things is the Laplace transform. So hit it. You only get one choice. Slap big fat L's on there. So you got Laplace transform of all of y double prime plus y. Should be the Laplace transform applied to delta t. Yep. Okay. Which means I need to go hunt down the Laplace transform table. So first things first, the left-hand side is a linear thing, right? It's a sum. So I should apply linearity. So if I apply linearity, I've got the Laplace transform of y double prime plus the Laplace transform of y. And this should equal, ooh, that one I can just look up in the table, right? What's the Laplace transform of delta t?
E to the minus s.
Tau is 0.
Yeah, tau is 0, right? You see that? So this should be really, I should be thinking of the Laplace transform of delta t minus 0, right?
Yeah.
You guys with me?
That's not true.
And so I should get what's in the table. So what we need to think, right, is we need to look for the Laplace transform of delta of t minus tau in the table.
Delta t minus a is e to the minus a, so actually d1.
So I think I got e to the minus tau s, right? Okay, so I have e to the minus s times 0, which is 1. Guys with me? Okay, that one.
Use the definition to break the double prime.
Okay, so yeah, go look up the double prime chunk, right? So you get s squared.
Big Y.
Yeah,
Big Y, right? The Laplace transform of y, minus s
Y. 0.
y at 0, which is 1.
1.
Cool. I'm just not going to write that. And then
Minus Y prime 0.
minus
So plus 2.
y prime of 0, so plus 2. And this is supposed to still equal 1.
We gotta add the.
Yeah, and we have to add another y.
Well, we gotta add the Laplace.
Oh yeah, and I lost the Laplace of y in my excitement for knowing the other side of the table, right? So I should add a capital Y and have equal y. Okay, so to check, that stuff there is the Laplace transform of y double prime. Y is pretty easily the Laplace transform of y, and 1 should still be 1. Pretty sure. Okay, that one.
Put all the Y's on one side, all the non-Y's on the other.
Yeah, like algebra. Right? So y's to one side, factor y out. So you got s squared minus 1 times y is 1 minus 2
What's that?
plus s. So I think I got s minus 1.
It's s squared y plus y.
It's s squared y plus y. See, and this is why you should never do algebra by yourself fast, right? The only reason I'm getting away skipping writing all the algebra steps down is that I have 10 of you or 12 of you watching very carefully, right? Okay, so I'm here, then what?
Divide.
Okay. So multiply everything by 1 over s squared plus 1. So you get y is,
S minus 1 over S squared plus 1.
okay, so you got s minus 1 over s squared plus 1.
And now take the inverse Laplace transform of both sides of the y.
Okay, so now you should hit everything with an inverse Laplace transform. And you have little y then is the inverse Laplace transform of rho.
Not far.
Not too bad.
Yeah, just split it into two parts. And
Yeah, so I need to split across the top. So I got s over s squared plus 1 plus the inverse Laplace transform of minus 1 over s squared plus 1.
I was
And you can
gonna
just,
say you could just do
yeah.
that.
Yeah, and you might notice that it probably was a better idea to pull that minus sign out front. So that's inverse Laplace transform and use linearity of the inverse Laplace transform, right? Okay, rad. Then you recognize those, and you say unto me, yo dude,
Cosine plus one.
T minus
you got cosine t minus sine t. And then you wonder to yourself, why didn't it seem like the delta made any difference? Yeah. Like, I was kind of expecting a discontinuous answer, right? Why? Because I gave this thing a good solid whack, right? Like, it was doing whatever it was doing, right? Like, y double prime plus y in the long. And then at time 0, I hit it with a hammer.
But I mean, think about a spring, it
But
just,
there's no damping function, there's no beater in there, y prime. So
Yeah.
it'd be,
But so it's bouncing along in space, right? And then I hit it with a hammer. Doesn't it do something different after I hit it?
oh, I see what you
No, necessarily.
mean. Yeah. Even an impulse you can-
Oh, I think if I hit it, it definitely better do something different. Otherwise, it's the same as not hitting it, right?
It depends where
So-
you hit it, I think. If you hit it at like the crest or the bottom or something.
I think it's still going to change, right?
It'll
Like,
change, but-
if I hit it while it's going up, it's going to go up some more than it would have. If I hit it while it's... Sorry, if I have it bouncing along like this, and now it's traveling up, and I give it a hit, right? It's not going to crest as high as it would have. If it's going up and I hit it the other way, it's going to go higher than it would have. You see that? Like, no matter how I do this, I'm adding or subtracting energy to the system.
Well,
Why is that not here?
well, if it was going up and you hit it, it would immediately, like, you get an instant derivative change. But you hit it at 0. And
And the Laplace transform happens
for 0 plus,
for 0 on.
yeah.
You guys see that?
So minus one not times.
So the reason that it's not seeming to affect anything is that you're hitting it at time 0, right? And so this y here, this solution, is valid for t's from 0 forward. You guys see that? So if I had hit it
So,
at a different time, then I would see that discontinuity because I would have an e over here to deal with when I inverse
so
Laplace.
this is like,
Oh,
And that would give me that unit step function.
it's like a resting spring, and then at 0 you hit it, and then you observe.
Yeah, so this thing was some kind of springing along, right? But what does springing along mean? Well, I'm really only considering that time after 0 because I just did that Laplace transform, right? So this thing's really only valid for t bigger than or equal to 0 anyway. You guys see that?
How could you even have a t less than 0? Like if you
Oh, you guys do this
negative
stuff all the time. Like, when what, like, so the amount of water in a tank is modeled by t plus 50. When was the tank at 25? Yeah, right, like 25 minutes ago, or 25 hours ago, or whatever. Like, yeah, there should be some meaning associated with negative time, but because I Laplace transformed everything, I kind of lost that meaning. See that? Okay, so,
So it's like
Cool.
having a resting tank of water, and then you can't really, you can't really model, the equation for going, for the volume going up until after the instant you start putting stuff in.
yeah, the Laplace transform kind of fundamentally assumes that things are starting at time 0, and before that, nothing really matters. Okay, cool with that? So it might be enlightening to do this problem again with a t plus 1, or a t minus 1 actually, right? Because I want it to happen at time 1. So if you do this with a t minus 1 in there, you would get an e term here, and then you would have some kind of initial behavior, and then some change.
So if you have t minus 1, does that mean you have e to the minus s times 1? Or is it e to the minus s times minus 1?
It's e to the minus s times 1.
Okay, so if you have plus 1.
Yeah, the
there-
minus sign is built into the.
Okay, that's what I thought. I just want to make sure.
Yep. So you could try that. That would be an interesting exercise. You would see something like something going on, and then plus a u of t minus 1, where something else happens, right? Like it's springing along, doing its thing, and then you hit it, and now something else.